The sun is the superpower of our solar system. A thermonuclear blast furnace erupting with massive explosions.
It can be the same amount of mass as Mount Everest coming out from the sun and flying out into space.
At 93 million miles away, it would seem that we're safe from the sun's wrath. But are we?
It matters, especially in modern times, what the sun is doing.
From the center of the sun, as it rotates around, is the kill zone.
With some experts predicting the most violent outbreak of solar activity in modern history, it's never been more important to understand the secrets of the sun. There are billions of stars in the universe, but one alone dominates our cosmic neighborhood: the sun. It's an infernal sphere of mostly hydrogen and helium, superheated into a plasma that burns at millions of degrees. Its surface rages with violent explosions as it spews out storms of deadly radiation millions of miles into space. Our sun is a type of star known as a yellow dwarf. Yellow because of the color of its surface, and dwarf because it's small for a star. But small is relative. Within its boundaries, you could fit 1 million Earths. In our solar system, there's simply no bigger star than the sun. At 1 million miles across, it's a massive celestial blockbuster.
The sun is really pretty huge. It dominates our solar system. Not only is it the biggest star in the solar system, it's the only star in the solar system. It's surrounded by a bunch of smaller stuff that we call planets and comets and moons. But the sun is our star.
Our star is an enormous source of heat and energy. It has a surface temperature of 10,000 degrees Fahrenheit and generates 380 billion megawatts of power. This dwarfs anything on the human scale. Hoover Dam in Nevada only generates 2,080 megawatts. In 1 second, the sun churns out more energy than has been used in all of human civilization. All that power in the blink of an eye. Incredibly, it's been burning this way for billions of years.
Early astronomers didn't quite understand how the sun could generate so much energy for that long a period of time. That was the first mystery, was really how the sun generates its energy.
In the early 19th century, scientists assumed that the sun worked just like any fire on Earth, that there was a source of fuel, perhaps coal, that was slowly burning away. But there was a serious problem with this theory.
I've got a fire in front of me here. If I want it to keep burning, I have to keep adding wood to it. This fire will last maybe an hour, unless I add some more wood. Now, if I had a pile of wood the size of the whole sun, and somehow enough oxygen to burn it, it would only take about 5,000 or 6,000 years to burn out. That's a long time, but it's not long enough to sustain life on Earth.
By the early 20th century, carbon dating of Earth rocks and fossils had proven that the sun was in existence and at temperatures warm enough to sustain life, not for thousands of years, but for 3 billion. If you wanted to build a fire that would last that long, you would need 72 trillion cords of firewood. That's 12,000 cords for each man, woman, and child on the planet. Clearly, there had to be some other process unknown on Earth that was powering the sun. In the 1920s, scientists found the answer to the puzzle in a process that would later be harnessed to fuel the hydrogen bomb: nuclear fusion. Fusion occurs when atoms are smashed together at a high rate of speed and literally fused. To get this to happen, conditions have to be just right.
For any interaction to happen, these two protons each has a positive electric charge, and so they would repel each other. So you've got to get them close enough together. And to do that, it's got to be hot, which means the particles moving very fast, and dense enough that they hit each other and they can get close enough together that they actually fuse.
The core of the sun is the perfect cauldron for nuclear fusion. It's the hottest place in the solar system at a sweltering 27 million degrees Fahrenheit, and it's also incredibly dense.
It's so dense, it's 10 times the density of lead. And you would think at that density it should be a solid, but it's not because it's so hot that it remains a plasma.
If you heat a gas to high enough temperatures, electrons fall off of the atoms and they float around in the soup. And so it has behavior that's different from what a gas would do. And so we have a different word for it, call it plasma.
To truly understand what goes on in the core of the sun, you have to find some way to imagine the almost unimaginable.
In addition to studying the sun, I also play pool. And the sun is a place where there are billions of particles colliding and interacting with each other. And it's really not unlike a cosmic pool table on an unimaginable scale. It doesn't matter how hard you hit a ball. You would never hit it hard enough to actually fuse that ball together with another ball. But there's so much pressure and such high density at the core of the sun that the two objects impacting each other will actually fuse.
In the sun, these objects are hydrogen atoms flung together by immense pressure to form helium atoms. In this fusion process, the resulting atom is slightly less massive than the ones that created it. The missing mass is given off as energy. Each second inside the sun, 600 million tons of hydrogen are fused into 595 million tons of helium. That 5 million tons of mass lost in the process is converted into energy equal to 1 billion 1 megaton hydrogen bombs. That's every second.
When you look out into the cosmos, the process that gives you the highest return of energy for free is what goes on in the centers of stars like the sun.
So we now know that the sun is powered by nuclear fusion. It's the only fuel that we know that can sustain the burning in the sun long enough to sustain life on Earth. Billions of years.
Sunlight. It's so central to life that we don't often give it a second thought. But how light gets from there to here turns out to be an incredible story. The energy created in the fusion process is carried out of the core by particles of light and heat called photons. They are what bring the warming rays of the sun to Earth. To reach our planet, these glowing travelers from our nearest star must first take a long, winding road through all the layers of the sun, like Dante journeying through the levels of hell. First, a photon enters the 185,000-mile-thick radiative zone. The region is so densely packed that the photon constantly bumps into other particles, like hydrogen and helium atoms. It struggles outward in a chaotic zigzag pattern that scientists call the random walk.
A photon can't escape without interacting over and over and over and over again, getting absorbed by atoms and re-emitted, and it can be absorbed and re-emitted millions of times. As the density decreases, as you get further up in the sun, it becomes easier, and the collisions and the interactions are less.
When it finally reaches to within 130,000 miles of the surface, the photon enters the convective zone, and the pace suddenly quickens. It's carried upwards by a kind of boiling, riding along in huge columns of gas at hundreds of miles an hour, taking only 10 days to emerge on the solar surface. The incredible journey is almost over as the photon lifts off through the wispy gases of the solar atmosphere. From there, it takes only 8 minutes for it to zip across 93 million miles of space to our planet. Incredibly, by the time sunlight actually reaches Earth, it's already been in existence for hundreds of thousands, if not millions, of years. For the sun, even a million years is a small blip in time. The simple, perfect disk of a sunset belies the long, violent history of our star. It is a ball of fire spawned billions of years ago in a massive explosion known as a supernova.
After this titanic explosion, where a star much larger than the sun exploded, there would have been a huge cloud of gas, many times larger than the solar system. And small knots of material would have gradually coalesced in this very large cloud.
About 5 billion years ago, some 10 billion years after the Big Bang that scientists believe kick-started our universe, this cloud started to collapse under the pull of gravity.
Our solar system probably arose from one such knot of self-gravitating gas that pulled itself together and gradually spun itself up as it pulled in, like a skater pulling her arms in during a spin, until the star and the various planets coalesced around it. Ultimately, when the star was dense enough, it would have turned on fusion and started glowing, giving off sunlight.
Why do scientists believe the sun was born from the ashes of a supernova? The evidence lies beneath our feet. Complex, heavy elements like the uranium we mine from the Earth to fuel our nuclear power plants could not have been forged in the sun. There is simply not enough heat in a star that size to create elements any heavier than iron. Heavy elements like uranium can only be created in a catastrophic cosmic explosion. Earth and the other planets in the solar system formed out of the same knot of gas that produced the sun. In this process, the sun hoarded 99% of the mass. This means it's the biggest object in our celestial neighborhood with the strongest gravitational pull. That's why everything else revolves around it. Of all the planets, Earth earned a privileged place in relation to the sun. If we were closer in, our oceans would boil away and the ground would be hot enough to melt lead. If we were farther out, our planet would be a frozen wasteland.
Sort of like Goldilocks and the Three Bears. Not too hot, not too cold, it's just right. Here we are at about 93 million miles away from the sun, and we're happy to be here. We're lucky to be here. And in some sense, we're here because it's the right circumstance for us to be here.
Earth may be in just the right place in the solar system, but we're also close enough to the sun to be a target of its fury.
This base on Mars is not an alien monument. Explore Mars in the Universe next week.
Thousands of mammoth explosions rock our sun every year. You might expect this explosive force to come from nuclear reactions in the core. But in reality, what drives all outbursts of solar violence is magnetism. Since Earth rotates as a solid, our magnetic field is simple. We have two poles, north and south. This is what makes a compass so useful for finding your way around the planet. But imagine if instead of two poles, you had 1 to 10 million. This is what happens on the sun. The sun's magnetic field is a tangled web because even though it's held together by gravity, the plasma doesn't rotate evenly. Plasma at the equator rotates once every 25 Earth days, while plasma at the poles takes roughly 35 days to circle once.
The sun has what we call differential rotation. You have all of this plasma that is really turning and churning, and that causes magnetic field lines to become twisted and intertwined and mixed up.
Although magnetic field lines are invisible, we know they exist on the sun by looking at features called coronal loops and prominences rising up into the solar atmosphere. Just as metal shavings line up in the presence of a simple magnet, these loops of plasma perfectly outline the magnetic structures that support them from below. These plasma arches are so tall and wide that you could slide a planet as big as Jupiter right through them. Sometimes magnetic fields can twist plasma in the sun's atmosphere into majestic helical shapes called flux ropes.
Magnetic flux rope is sort of like a slinky. The magnetic field line is wrapped around many times in a helical structure. And when you have highly twisted magnetic field lines, it carries a lot of stored free magnetic energy. And sometimes it will even kink in on itself, which gives it even more stored magnetic free energy.
These plasma prominences can last for weeks or months, but eventually the stored up energy has to be released, and the mass is flung off into space. Where the sun's magnetic field is at its most twisted and complex, heat bubbling up from below is capped, and the material is cooled by as much as 1,000 degrees. What results are relatively dark blemishes on the solar surface called sunspots. Sunspots are only dark in relation to the bright material around them. If you could somehow suspend one alone up in space, it would shine 10 times brighter than the full moon. These apparently tiny blemishes are actually plasma craters the size of the entire Earth. Galileo was one of the first modern scientists to observe sunspots. Using a telescope, he projected an image of the sun onto paper and traced it. He realized that the blemishes were moving across the face of the star, which was the first indication that the sun rotated. Not only does the sun rotate, but sunspots themselves can actually spin like hurricanes on the solar surface. And when they do, their magnetic field lines become extremely twisted. Twisted magnetic field lines mean more energy, and more energy means the potential for huge eruptions.
Think of a rubber band as a magnetic field line. If you twist it, and you twist it enough, it's going to have all that energy, and when you let it go, it's going to release. If you just take an untwisted rubber band and release it, it's not going to fly.
When a sunspot unleashes its magnetic energy, what results are the most colossal explosions in the solar system, solar flares. A single flare releases as much as 1 billion megatons of energy, the combined power of 1 million volcanic eruptions on Earth.
They appear as these very bright regions, and they're so bright because the temperature is so high, on the order of 10 million degrees. And they can last for hours, but the energy is massive.
The whole explosion is equivalent to millions of nuclear bombs leaving the surface of the sun all at once.
Solar flares don't just explode out into space. They also funnel high-energy particles down to a layer of the sun called the chromosphere, where they quickly transfer their energy like a cue ball striking the rack in a game of billiards.
So the cue ball acts like one of these very high energetic particles coming from the flare region. The cue ball smacks very quickly into the 8-ball rack. And once it impacts that head ball, it's going to transfer that energy to the balls behind it, and then they will all fly out because the energy is transferred to all of them.
If a large flare shoots enough high-energy particles at once, strange things start to happen. This is actual footage of a sunquake.
In 1998, there was a solar flare up in the corona that was so powerful that the material flying down toward the surface of the sun actually slapped the surface and caused ripples to spread out from there.
While they may look like ripples on a pond, these are actually waves 2 miles high, traveling at a maximum velocity of 250,000 miles per hour. The 1998 sunquake would have measured an 11.3 on the Richter scale, more than 1 million times stronger than the 1989 earthquake that shook San Francisco. In order to shake the surface of the sun that much, the solar flare had to release a colossal amount of energy.
It turns out it's almost the same amount of energy as if you covered the entire landmass of the Earth with dynamite, about a yard thick, and set it all off at once. So these explosions are not small.
Earthquakes aren't the only natural disasters with equivalents on the sun. A flare can also kick off a solar tsunami, as waves of plasma in the sun's atmosphere rocket out at 700,000 miles per hour, spreading around the entire face of the star in a matter of hours. While sunquakes and solar tsunamis pose no danger to Earth, the violent action of a flare frequently triggers dangerous eruptions called coronal mass ejections, or CMEs. In a CME, energy from a flare flings a blob of highly charged radioactive plasma out of the solar atmosphere.
Coronal mass ejections range in speeds, but they can occur as quick as 800, 900 miles per second, which is extremely fast, and they expel a massive amount of material. It can be the same amount of mass as, say, Mount Everest coming out from the sun and flying out into space.
Where does this blob of superheated radioactive plasma go when it leaves the sun? Sometimes it sails out harmlessly into space. Other times, it may head closer to home. Coronal mass ejections from the sun are perhaps the most dangerous threat you've never heard of. Also known as solar storms, they hurl large masses of supercharged particles across 93 million miles of space. Most take several days to travel from the sun to the Earth, but some rocket across the solar system at up to 6 million miles an hour, reaching our planet in less than 16 hours. These storms can induce currents in the outer atmosphere, knocking out satellites and cross-country power grids, and carry the potential to wreak just as much havoc on our infrastructure as a hurricane or tornado. But who on Earth is keeping an eye on these potentially hazardous cosmic blasts? This is the headquarters of the National Oceanic and Atmospheric Administration, home to the U.S. government's National Weather Service. Their daily forecasts, watches, and warnings are essential information for everyday life on our planet. But there's a lesser-known group of forecasters working here in a special division called the Space Environment Center.
Our primary job is to monitor the sun and to put out the alerts and watches and warnings for solar activity.
Good morning, welcome to our 8:10 briefing. We had one long-duration C flare from the east limb. That's possible CME. We have not had protons, but we have had electrons.
One thing to note is that this region produced all the activity in December, so things might be picking up here in the next couple of weeks.
These space forecasters are on high alert for solar storms that might disrupt life on Earth. Solar storm clouds are made up of charged particles, so they're initially diverted around the planet by our magnetic field, just like waves breaking around the bow of a boat.
That turns out to be very important, because if it impacted the outer atmosphere directly, it would knock little bits of the atmosphere off into space. One reason why Mars doesn't have an atmosphere is that it doesn't have a strong internal magnetic field. And so gradually, over millions or maybe billions of years, the atmosphere was gradually knocked off into space by the influence of the solar wind and by CMEs that came past the planet.
But our magnetic field is not the perfect force field of sci-fi movies. Some particles can penetrate it, charging up the upper atmosphere. Solar storms will even bend and break the magnetic field lines on the far side of the Earth, allowing charged particles to zip back down the field lines toward the north and south poles. Extremely powerful storms distort the magnetic field even further, inducing electric currents that span the continents. When this happens, technology like long-distance power lines can become overloaded.
It can cause damage to transformers at either end of the line. In fact, in 1989, most of the Canadian province of Quebec blacked out because a transformer was blown out by a solar event.
If we have that storm that hits our communication system, it hits our power companies and all these things that we depend on, there's all kinds of chaos that can lay out there.
If power operators have time to react, they can reduce the current being sent over their wires and avert disaster. Satellite operators can also prepare for the onslaught with proper warning.
When there's a big space storm coming, they'll actually put some of their satellites to sleep so that the storm doesn't cause an electrical short or otherwise somehow knock out the satellite. So the more warning time they have, the better.
We wouldn't go sailing unless we knew what the weather was going to be. Similarly, when we have a large system like a power system or a telephone grid that can be affected by the weather in space, we need to know what the weather's going to be so that we can try and mitigate it.
Solar storms can also disrupt high-frequency radio communications used by aircraft. In the 1980s, Air Force One was transporting President Reagan on a trip to China when a solar storm struck. All communications were lost for several hours, effectively severing the head of the United States government.
The urgency is just like our Earth's weather. When we have a tornado warning, we know the urgency to get that out to the public, to let people know that this is happening. The same thing is with space weather. Users of this information need to know it, and they need to know it now. Just a few hours back, we experienced a coronal mass ejection. We want to see where this blast is going out, and then we can measure that and see how long it might take from that to reach the Earth from the sun. We're seeing a very huge explosion of material that's coming out, and if you look at this small image here, there's the sun that's covered up, and look at the mass that's being thrown out into space. So it's huge, very huge.
Because magnetic field lines emanate from the north and south poles, energy from solar storms has easy access to those regions. For that reason, experts worry that airplane passengers flying over the poles during a powerful storm might be exposed to harmful levels of radiation, perhaps a dose equal to 100 chest X-rays.
It's not something that we want to mess around with because we never know when that radiation might all of a sudden become a lot more intense while there's an airplane in the sky.
The threat from solar radiation is just one more reason scientists keep a close watch on our sun.
It matters, especially in modern times, what the sun is doing. Earth is not an island. We are a participant in the activities of the solar system.
Sunspots are the triggers for most severe solar storms, so forecasters track them carefully as they rotate across the surface of the sun.
Location, location, location. We see coronal mass ejections all the time from the sun. A lot of them are as the sun is rotated around or from the backside of the sun. That would not be faced toward the Earth, so that would be less of a concern. As the sun rotates around and that active region gets more into the center of the disk, looking at us, then that's when we would be concerned with. From the center of the sun, as it rotates around, is the kill zone.
As the sunspot rotates around and begins to face directly at Earth, that's when we really have to worry about a storm. If a big storm lifts off then, it can aim directly at Earth and the full force of the storm slams into the planet.
It's like a shotgun aiming at a target. The more dead on the shot, the more likely serious damage will be inflicted. With great danger also comes astonishing beauty. Solar storms generate majestic planetary light shows. The shimmering curtains of color called the aurora. Auroras work like neon signs on an enormous scale. In a neon sign, electricity introduces charged particles into a gas-filled tube. The particles in the gas are excited and start to glow. If the tube has only neon inside, it will glow red. By adding other gases, like argon, a whole range of colors can be produced.
The neon sign is driven by the electric field inside the tube, whereas the aurora is actually driven by the magnetic field and energy from the sun.
As the energetic particles in a solar storm stream along Earth's magnetic field towards the poles, they excite elements in our atmosphere, causing them to glow. Oxygen molecules emit a green or red color, and nitrogen emits pinks, blues, and violets. While these ghostly lights are usually confined to the poles, extremely strong solar storms can drive them closer to the equator. In 1859, a geomagnetic storm ignited by a huge solar flare created auroras as far south as Rome. The 1859 storm was an unusually powerful event that some have called the perfect solar storm.
The 1859 storm taught us a little something about what the sun can do. The storm was so intense and the alignment was so perfect that it simply overwhelmed Earth's natural defenses.
A huge solar flare erupts on the surface of the sun. Less than a day later, and 93 million miles away, the wires that carry communications across the Earth begin to spark. Business grinds to a halt worldwide as wildfires are ignited by the smoldering lines. At the same time, colorful auroras light up the skies of cities around the globe. Earth has just been visited by the perfect solar storm.
The sun kicked up this just incredible solar flare and a massive amount of energy headed towards Earth.
Not only was this storm one of the two most powerful on record, it was also one of the fastest. Ejecting from a sunspot aimed directly at Earth, it raced from the sun to our planet in less than 18 hours.
Now it takes a really fast rocket ship years to get to the sun. This storm, this cloud of electrified particles, managed to get here in less than a day. That's incredibly fast.
Fortunately, the perfect solar storm took place in 1859, when the only technology vulnerable to the onslaught was the telegraph. Since the era in which we have become dependent on high technology, we've yet to see another perfect solar storm. The question remains, could it happen again?
What if we have another one like that? Can we have another perfect storm? Well, I'd say yes, we can. There's no doubt about that. The effects that would be on us today compared to 1859 could be devastating.
The effects on Earth and on our communication systems, we don't exactly know. That's the scary part.
It's likely that our modern technologies would be battered like beachfront houses during a hurricane. Imagine if we lost all the satellites that relay cell phone calls, television signals, and bank transactions. And what if, at the same time, the failure of power grids cascaded whole regions into darkness for hours or weeks? If these essential services couldn't be restored quickly, chaos wouldn't be far behind.
It would definitely be a ripple effect upon society and every man and woman and child that lives on this earth.
Solar storms can be as hard to predict as hurricanes. While forecasters lack the technology to foretell the next perfect storm, they do know that one would be more likely to hit at the peak of the sun's 11-year sunspot cycle.
What happens is the sun reverses the direction of its magnetic field every 11 years. So in 22 years, it reverses and comes back to where it was.
As we near the reversal every 11 years, the number of sunspots increases, and there's a spike in solar activity.
We call that period solar maximum. And those periods are interspersed about 5 years apart from periods we call solar minimum.
So you have this 11-year back and forth between the sun being sometimes very ferocious and it goes crazy and it's like the 4th of July with fireworks all the time. And then it starts to ramp down, and for a few years it gets quieter until we get to a low point where there's a firecracker now and then, but not a lot going on.
Just like hurricane seasons, solar maximums vary in intensity. Some produce many more powerful storms than others. Although we're currently at solar minimum, scientists are watching carefully to see what mayhem the next solar max might unleash.
So the last solar maximum was in about 2001, and so the next one ought to be about 2012. But there are different predictions. The whole field of solar physicists is basically waiting with bated breath to see what actually happens.
There are some wildly divergent opinions on what's going to happen. One group is suggesting that this next solar cycle could be the strongest in modern times.
If those predictions are correct, Earth could be in for a wild ride.
We might have to worry about a repeat of the 1859 event. If that were to happen today, it would wreak untold damage.
We're going to learn a whole lot about what can happen to modern technology when the sun blows its top.
Much of the violence in the sun erupts here, in the hellish outer atmosphere known as the corona. This region has long held one of the great solar mysteries, because even though it's 500,000 miles from the heat-generating core, it burns at millions of degrees. This seems to violate the very laws of physics.
That's very strange. I have a thermometer here. If I hold the thermometer close to the fire, it reads a very high reading. Where the probe is right now, it's over 200 degrees. Now, if I pull the probe out a little farther from the fire, okay, it drops down to about 90 degrees. Now, the farther I get from the center, the cooler it gets. In the atmosphere, the corona of the sun, the temperature soars as hot as the core. That's as if I were to say, well, way off behind me there, the heat from the fire is as hot as the fire itself, even though it's very far from the fire.
What force could possibly cause the superheating of the corona? The answer will rock you. The hellish solar corona rages at millions of degrees. For centuries, scientists have been baffled how anything so far from the sun's core could still burn so hot. Recently, as improved satellites offered a closer view of the solar surface, clues began to emerge. Below the corona, the sun's surface is literally boiling.
The reason is that the entire surface of the sun is covered with convection cells, hot material from the inside of the sun. It rises up through, reaches the surface, cools off by glowing, giving off sunlight, and then sinks back down. Each bubble of material that comes up is about the size of Texas. It spreads out across the surface, cools off, and sinks down in 5 minutes. So that's a tremendously violent process. Well, that's happening in literally almost 1 million places over the entire surface of the sun all the time, around the clock, 24/7.
This boiling isn't only violent, it's also extremely loud.
The sun is a tremendously loud place. If you could imagine covering the entire surface of the sun with speakers being driven as hard as the loudest rock concert you've ever been to, that would be comparable to how loud it really is on the surface of the sun.
The sun's churning surface creates enough sound energy to superheat the corona to millions of degrees. Scientists believe that a combination of these sound waves and energy from the sun's magnetic field is responsible for the extreme temperatures found in the corona. The only time you can actually see the corona from Earth is at the climax of one of the most dazzling displays in the solar system, a total solar eclipse. Before scientists understood them, these awe-inspiring events instilled only fear. The ancient Chinese believed that a dragon was devouring the sun. So what's really happening in a solar eclipse? In simplest terms, it's when the moon blocks our view of the sun.
Imagine that you're sitting in the movies watching very happily something going on the screen, and then somebody in the row in front of you comes across and blocks your view. In the movie theater, you might not want that person to come across in front of you, but at an eclipse, we're very lucky to have the moon come across the sun, and we're lucky to have it come right across the middle.
We're also lucky that the moon, although it's 400 times smaller than the sun, is also 400 times closer to us. This cosmic coincidence means that the two objects just happen to be the same apparent size in our sky, which allows for one to completely block out the other. This magnificent cosmic event only happens when the path of the moon intersects the line between the Earth and the sun. The moon's orbit is tilted slightly, about 5 degrees. If it wasn't, we would have an eclipse every month.
And then we'd be bored. But we're not bored because most months the moon goes above or below the place where the line goes from the Earth to the sun.
So instead of one every month, we get a total eclipse somewhere on Earth about once every year and a half. As the moon slides in front of the sun, it casts a shadow onto the Earth. The outer part, where the shadow is fainter, is called the penumbra. If you're standing within the swath traced by the penumbra as it moves along the Earth's surface, then you'll see only a partial eclipse. But travel to a spot within the path of the dark inner shadow called the umbra, and you'll experience the majesty of a total eclipse. There's another option if you can't travel to the path of totality. Wait in one place long enough, and a total eclipse will pass right over your head about once every 300 years. The sun, that shining star of our solar system, is capable of both astonishing beauty and ferocious violence. It seems impossible to believe, but it won't be around forever. Eventually, even the sun must die.
The sun has a fixed amount of fuel in its core. It is undergoing fusion at a rate that you can calculate. You say, here's the rate it's using its fuel. Here's how much fuel you have. So it's a simple calculation to show when the sun will die. And that's in about 5 billion years.
Well, unfortunately, the sun will not go out with a bang. It is too small to erupt in a supernova. However, stars do a peculiar thing. They're one of the few things around that get hotter as they cool off.
As it exhausts its hydrogen fuel, our nearest star will cool and gradually collapse under the force of gravity. Energy from this collapse will start heating up the core again to hundreds of millions of degrees, hot enough to start burning helium. Under the extra heat of the helium burning, the star will expand into a monstrous orb called a red giant.
It gets so big, it will engulf the entire orbits of Mercury, Venus, and Earth. You don't want to be around for that. You want to be planet hopping your way to safety long before this happens.
The Earth is likely to change its orbit slightly as the star expands so that it won't be engulfed. Still, talk about global warming, you wouldn't want to be there.
The outer layers of our sun will eventually become so unstable that they will fly off into space, leaving behind a small core about the size of the Earth.
So remember, we've shrunk most of the sun, which is 1 million miles across, to the size of the Earth, which is more like 6,000 miles across.
Our once great star reduced to a slowly cooling cinder.
And life as we know it on Earth will cease to exist. And that is the death of the sun.
All of this is bad news for the human race. But look on the bright side.
We've got 5 billion years to prepare for this disaster.
For now, humanity basks in the glow of a sun in the prime of its life. Science has uncovered many of the secrets of our nearest star, but we remain awed by its beauty and ever more wary of its wrath.